Electromagnetics aren't the only actuation game in town. There are other forms of transduction that you can use in order to create some kind of physical output in the world, to provide some velocity, some force or torque on the world. So one example of that uses thermal energy. And so the basic idea behind this is if I have a chunk of some material right here, and I run a current through it to heat it up, or I heat it up through some other means, I'm going to actually expand that block of material. This is obviously kind of an exaggerated drawing right here, but I'm going to have a strain based on my temperature change that I get here, where that thermal strain is equal to alpha times delta T, where alpha is a coefficient of thermal expansion, or CTE. To give you one example, aluminum is about 23 times 10 to the minus 6 meters per meter, or 23 microstrains per degree C. So this is typically a fairly small effect in terms of creating displacement in the world. One way to exaggerate that effect is, instead of using a material like copper or aluminum or silicon, I could actually use a shape change material or shape memory alloy material like nickel titanium alloy. So for shape memory alloy or an SMA material, I might have my delta T will result in a phase change. So at low temperatures, I have what's called the Martensite phase. And I have two versions of that. I have this kind of undeformed version that looks like this, and this is kind of the structure of the atoms within the alloy. And if I deform it, I get something that looks a bit like this. And at high temperatures, everything straightens out in the austenite phase right here at the higher temperatures. So by going from a low temperature to a high temperature, I'm actually creating a strain in the material that's not due to necessarily that coefficient of thermal expansion, but due to an actual phase change in the material. Right? My atomic structure is going from this to this, for example. And using that, I can actually create a fair amount of force and a decent amount of strain using this thermal energy. Great way to get thermal energy is running a current through this, right, and just using the power dissipation in a resistor. Right? My power dissipation is going to go as proportional to I squared R. Right, so I can think of the heat in my piece of metal, or my piece of alloy, as at least the derivative of that heat going as I squared R. So SMA has some great advantages. A big one is going to be in power and force per mass of actuator, or I can think of that as specific power or specific force for the actuator, or watt per kilogram or newton per kilogram for this particular actuator. And these are often used in situations where I really care a lot about, for example, the mass of the actuator. So a lot of UAVs might use some kind of SMA actuator to control, for example, a flap on a UAV, because I can get high forces and high powers for very, very lightweight control in comparison, for example, to a servo. Also relatively simple to use. All I need is to provide basically a current to generate the heat. Right? I run a current through here that generates the heat, and that's what's going to switch me between my phase states right there. So they're fairly simple to set up some kind of power circuits or electronics to actually provide that current. Disadvantages aren't really numerous, but the primary disadvantages are going to be around efficiency. Right? I'm still going to waste a lot of energy by heating this in this way, and I'm also not going to be able to move this very fast, so these typically are going to be somewhat bandwidth limited. Sorry, that should be bandwidth is low. And sometimes displacement can also be a disadvantage. So typically I'm getting something like 3 to 5% strain between these two states, which is pretty large compared to what I can get just with a normal chunk of material and heating it up. But, you know, still not a lot compared to what I might be able to get from a solenoid or some electromagnetic actuator. And so there are ways of getting around this. I can coil this whole thing up, and even though I have a fairly small strain still, because I have this coil system, I can get a fairly large displacement for my actuator in the end. My basic use case for SMA as an actuator is pretty simple. The first step is I need to train the SMA into the kind of shape that I ultimately want it to be in. I can also think of this as actually the shape memory portion of the SMA. And I typically do that at pretty high temperatures as well. But say I've just kind of trained it into this kind of straight line material. And at this point I'm going to reduce the temperature beyond this anneal step at 550 degrees C. So I'm now in this twinned martensite phase. My next step is actually going to be to add some mechanical load to my SMA. So imagine my just wire of SMA here, and I've added a mass at the end to kind of strain that. And at this point I'm going to be in that deformed martensite phase. And this is where things get cool. So my next step is to heat the SMA, and I can do that through joule heating, running a current through it. And that's going to return it to its memorized shape, or basically put it in the austenite phase. And then I can basically go back and forth between these steps, go between the deformed martensite phase to the austenite phase, and move this mass up and down. So that's the basic approach at how I would use this SMA wire. I can buy this. It's very easy. Nitinol, nickel titanium is a very common version of SMA. There's a lot of stuff out there. It's fairly inexpensive and easy to use. Another particularly special material that gives us some extra or some additional ways of actuating are piezoelectrics. So piezoelectric materials in general can either generate an electric field when they're deformed, and this is called the direct piezoelectric effect, and clearly important for sensing, right? So I might be able to use this as a pressure sensor or strain sensor or something like that. The second use case is that I can deform the material under an applied field. And this is the indirect piezoelectric effect that I can use for actuation. So the special thing about piezoelectric materials is that they have these dipoles inside of them, and they are, after I've pulled the material, they're oriented all in the same direction. So if I'm to close this switch right here, I'm actually going to get a displacement. I'm going to create a stress and a strain in my material here because I have positive charges coming out of my supply, negative charges out the other side, and those charges are going to basically compress those dipoles together, right? And so I'm going to get a strain in my material because of that. So these particular materials, piezoelectrics, can give me a lot of stress. They're typically very limited in strain, even more so than the shape memory alloys. They oftentimes require fairly high fields. There's fairly high voltages applied to them, somewhere on the order of a couple hundred volts. But they're fairly easy to work with. They're just a ceramic. They're not terribly expensive. And so that's why you see them show up in things like the piezo buzzers in the kits that you get with your Arduino.